Thank you for the introduction, and thanks as well to the organisers for the invitation to speak here. Yeah, so today I'm going to be talking about two areas that we've heard a lot about this week. So I'm going to be talking about some ideas from robust statistics, and I'll also be talking about differential privacy. So this is joint work with my two collaborators, Mengchu Li and Yi Yu, and all three of us are at the University of Warwick. So as I said, we've heard quite a lot about differential privacy this week, so I won't spend too much time motivating the framework. But just a quick recap: this is a framework that you use for data analysis when the data that you want to analyze contains highly personal or sensitive information on individuals, and those individuals would not want this data to be made public. So it's a way that you can kind of still analyze data, but without revealing too much of the data to the general public. Most of what we've heard so far this week on this topic has been about what's called the central model of differential privacy. So this is where you can calculate things like medians of your data, and then you can randomize these medians and release them. I'm going to be talking about local privacy, which is slightly different. So in local privacy, what we do instead is we randomize the data as it's collected, which means that we're working with kind of randomized data sets rather than randomizing standard statistics. So this is a cartoon that's perhaps more appropriate for this model. We're adding noise directly to the data set to come up with a randomized, secure data set, which we can then analyze. Okay, so some brief notation to start. So I'm going to be writing X for raw data. So this is data that contains potentially sensitive information that we don't want to release to the public. I'm going to write Z for privatized data. This is data that we think of as being safe for public consumption. This is stuff that can be published widely. And a privacy mechanism is denoted by Q. This is what tells us how to generate Z from X. So formally, this is conditional distributions, such that if we observe data X equals X, then we generate Z according to Q given X. So this is a very broad idea. This is saying that we can protect people's data by adding noise, but this is quite a hard thing to quantify. There are lots of different ways that we could add noise to data. There are different amounts of noise that we could add to data. And so we need a way to measure the amount of privacy that a certain mechanism will give us. And that's where the specific topic of differential privacy comes in. So there could be lots of different ways. In fact, there are lots of different ways of measuring how much privacy a mechanism gives you. Differential privacy is this way here, and it has prevailed as the most popular way of doing this. So if we've got a mechanism Q, we think about all possible inputs to this mechanism. So we think about having two data sets, X and X prime. And if these data sets are neighboring in the sense that they only vary in a single observation, then we require this likelihood ratio to be bounded by a quantity which I'll write as e to the alpha. So this has to be bounded for all possible events A. Just beware. So usually in the privacy literature, people use epsilon for the privacy parameter. Here I'm using alpha. There will also be epsilons which represent contamination proportions, so try not to get confused by that. Here I'm writing alpha for the level of privacy that we want to impose. And you can note straight away that for small values of alpha, this is a stricter constraint, and for larger values of alpha, this is a weaker constraint. Okay, so we say that if two data sets only differ in one coordinate, then the randomized data's distribution cannot change too much. This is, as I said, probably the most popular way of measuring privacy, and this has been implemented in very large scale applications. I'll note two in particular, probably Google Chrome and in Apple iPhones. These two are prime examples of where the privacy is applied locally. So where data is collected randomly, before it's analyzed, the data is already randomized. Okay, so as I said, we're looking at the relationship with robust statistics, and you can kind of see in the definition that I've shown already that there are some links here. So we've seen already that in differential privacy, we're limiting the effect that any single input can have on our output. And that kind of reminds us of what we would do in classical robust statistics. In robust statistics, we would often hope that our estimators are not affected too much by outliers, which means that they're not affected too much by small numbers of inputs. So this is an indication that there's work to do to understand this link. And in fact, in the central model of privacy, there has been quite a lot of interest in these connections. So I'll just cite a few here. So we have stuff back from 2009, which is very near the start of when differential privacy was introduced. Marco, who's in the audience, has written some interesting work about this. And then there are two more recent references that I think Ilias was referring to earlier when he said that there are ways of kind of turning black box robust estimators into privacy mechanisms and vice versa. So there has certainly been some interest in these connections in the central model of privacy. For example, just one basic connection, which John talked about in his lectures, is that if you have an estimator which can be written as a function of the data that has a bounded global sensitivity, then you can add Laplace noise to your estimator proportional to the global sensitivity, and this will give you alpha differential privacy. As John was saying, this is quite a basic notion. You can do many refinements of this, but this is just one indication of the links. So we're looking at local privacy instead. So this is where you have a graphical structure that looks something like this. So you have your raw data, and your raw data is never seen by anybody else apart from you. This data is randomized as it's collected. In full generality, we can allow some interaction between individuals. So this means, for example, that individual X2 could randomize their data based on the output from individual 1. They don't see individual 1's raw data, but they do see their randomized data. So if you restrict to mechanisms that satisfy this kind of graph, then the definition of differential privacy reduces to something like this. You can think of having one privacy mechanism per person, and it has to satisfy a similar likelihood ratio condition. Okay, so that's kind of a brief introduction to differential privacy, and specifically local differential privacy. As I said, we're looking at robust statistics. So how am I going to look at robust statistics? The way I'm going to do it is by looking at Huber's contamination model. There are lots of different ways of introducing contamination. This is one that is very classical and goes back to the 60s. So instead of having IID data from our target distribution P, we assume that we have IID data from this mixture distribution, which means that we have a proportion 1 minus epsilon of our data coming from our target distribution. We think of that as clean. And then we have another proportion of the data, which is hopefully small, which is coming from some arbitrary outlier distribution. And we will make assumptions about our target distribution as is standard in all kinds of statistical problems, but we will make no assumptions about the contamination distribution. Okay, so I just should say at this point, there are kind of two choices that you can make if you want to simultaneously study local privacy and contamination. What I'm going to be doing is saying that we have data generated from this mixture model, which is then privatized. So that's saying that contamination occurs before privacy. You could also look the other way around, so you could consider having clean data that is then privatized, and then perhaps the output from these mechanisms is manipulated. And that is something that has been looked at in previous work, including from Julian in the audience. I should say as well, the results are quite different. So broadly, what we'll see is in the framework that I'm looking at, the results are quite simple in that you have this very clean decoupling between the difficulty due to privacy and the difficulty due to contamination. But if you consider things the other way around, then you can get some interactions between these two effects. Okay. This is just to introduce some notation. I'm not going to use this too heavily, but this is really just to say that I'll be thinking about problems in a minimax framework. This is very much like a standard minimax framework, but the difference, probably the main difference, is that we have two in FEMA here, whereas you would often only have one in a standard minimax framework. So we're quite used to looking at in FEMA over all possible estimators, But here, our estimators are based on the output of a privacy mechanism. And in LDP, or in DP more generally, we're also allowed to choose what mechanism we use. So we have an infimum over all privacy mechanisms that satisfy our constraints. So we're always choosing a pair of objects. We're choosing how to randomize our data and then how to use the output of that mechanism. Often, actually, the way that we choose the mechanism is going to depend very strongly on the specific task that we want to solve, but that's something we'll see later. So we have a relatively standard Minimax framework here, except that we're also allowed to choose the privacy mechanism. Okay, so just some brief clues from the literature that there are connections between these areas of local differential privacy and Huber contamination. So if we go back to thinking about a classical model, there are these very nice series of papers. There's this very nice series of papers by Donahoe and Liu, where they show that in kind of broad generality, you can think about minimax risks as being controlled by Hellinger modulus of continuities. So these are the papers called geometrizing rates of convergence. So you can see that for many estimation problems, this is a crucial quantity. You see how much you can vary a parameter under the constraint that your distributions are close in Hellinger distance. However, if you want to look at Huber's contamination model instead, so for example, as was done in these two works, what changes is that instead of looking at the Hellinger distance, you should really be looking at the total variation distance. So that you get similar results in similar kinds of generality that say that a total variation modulus of continuity is the important quantity to look at if you want to measure the minimax difficulty of a problem. So that's what you have in Huber contaminated models. But also you get the same behavior in a certain class of LDP problems. So this was a more recent work by Angelika Roeder and Luca Steinberger, which showed that again, the total variation modulus of continuity is what's important under alpha LDP. So this is a clue that there's some connection between these areas. If you either introduce contamination or privacy, the Hellinger metric changes to the total variation metric. Okay, so what I'm going to do, what we did in this work, is we first presented a very general lower bound on this minimax risk, and then we showed that we can match this lower bound in a few canonical statistical problems. So I'll just give some ideas of the lower bound. The lower bound is very simple, so it won't take me long to give some ideas. So we have two parts to our lower bound. We have one part that's to do with contamination, and we have one part that's to do with privacy. This part is to do with contamination, and of course, it appears in previous work. So we're using a lot of ideas from the literature here to kind of build up our results. So this is a nice fact about Huber contamination models. So if we have two distributions, R0 and R1, that are close in total variation distance, close meaning it's bounded by this quantity here, then we can always find contamination distributions which make these look exactly the same. So if the total variation distance between R0 and R1 is bounded like this, those distributions are indistinguishable when we introduce contamination. So by using a LeCam 2-point lower bound method, this immediately tells us that we have a lower bound in terms of this modulus of continuity. So any distributions R0 and R1 that satisfy this constraint are indistinguishable, so it can't be possible to estimate theta with better accuracy than this. The data would look exactly the same under either of these two distributions, so we certainly can't estimate theta any better than that. So this is a very simple, it's a very nice, powerful idea. Once you know it, it's very simple to explain, and this gives us 1/2 of our lower bound. The other half is basically trivial. We just say that the problem with both contamination and privacy is at least as hard as the problem with just privacy and no contamination. And that's what's giving us this first term in the lower bound here. The second one is what was on the previous slide. So in itself, I wouldn't say this is a very interesting bound. It's very easy to prove. But what's interesting is that we can match this lower bound in all of the in fact, in all the examples we considered, we can match this lower bound. So the problems that we considered were the following 4. So we considered simple hypothesis testing, mean estimation, density estimation, and median estimation. The reason I've put simple hypothesis testing in brackets is that this is not exactly true in that model. When we think about testing errors, it's often easier to think about separations rather than the risks themselves. So morally, this is kind of true in that we see a decoupling, but it's, strictly speaking, it's not true. But we can prove something similar. So we have a general lower bound which suggests a decoupling between these two aspects of the problem, and we're going to show that this is tight, at least in the problems that we considered. So what this tells us, the way I interpret this, is that these two aspects of the problem are quite well aligned. At least in the problems we considered, it was always possible to simultaneously be optimally robust and optimally private. There was no trade-off between these two things. We could always do both of them at the same time. And the difficulty of the problem is just the hardest of the two individual problems. Okay, so having introduced the work, I'll talk about simple hypothesis testing. So the rest of the talk is going to be about upper bounds. It's going to be about methodology. Okay, so simple hypothesis testing. By simple hypothesis testing, I mean point hypothesis testing. So I mean that our null and alternatives are specified. So we have some distribution P0 and some distribution P1, and we just want to test whether our target distribution is equal to P0 or whether it's equal to P1. Now, classically, this is, as I said, these are hypotheses that are point hypotheses. Because we've got contamination, they effectively become composite hypotheses because our data generating distribution is a contaminated version of these distributions. But classically, these are simple point hypotheses. And it's well known from Neyman-Pearson theory that to solve this problem in a classical framework, you would use the likelihood ratio test. This is exactly optimal, and so everything's very, very simple there. It's also well known that the likelihood ratio test is very sensitive to contamination, at least it can be. And if you want to be optimal in Huber's model, then you should do something else. In fact, when Huber introduced his model a long time ago in the 60s, he also found the exactly optimal test to compare these two hypotheses under contamination. This is not that test. That test relies on knowledge of epsilon, so it needs you to know how much contamination there is. I want to avoid that, so I'm using something else instead. And the advantage of this is that you don't need to know how much contamination there is to use this test. So this is sometimes called the Sheffey test, and we calculate this test statistic on the left and we compare it to the threshold on the right. And you can see quite easily that this test statistic is very insensitive to any individual data point in the sample. So you can see that if we change one data point, the most we can change this test statistic by is 1/n. So this is very insensitive to outliers, which is what we want. So that's very good from a contamination point of view. A reason why this is very good from a privacy point of view as well is that it's very easy to privatize binary information, where this test effectively reduces each data point to a single bit. We're just checking whether xi lies in a given set or not, and that information is very simple. It's very easy to privatize. We're choosing the set to satisfy this equality here. You can write this down explicitly, but I haven't. And we can think of this set as the set that kind of maximally discriminates these two distributions. We're just counting how many points lie in this set to do the Sheffey test. So this is what you would do without privacy, just under a contamination model. And this is a private version of that test. So as I said, it's very easy to privatize. Back way before people were talking about differential privacy, Warner had a work on effectively doing local differential privacy or using local privacy mechanisms that he called the randomized response mechanism. And with this data, with binary data, it's very simple. So if you think about this, really there isn't much else you can do. All you can really do with binary data is randomly flip the bits or not. And that's what this mechanism is saying. So it's saying that with this probability here, we keep the binary bit the same, and otherwise we flip it. So we say that if it's 1, it becomes 0, and vice versa. This probability is, of course, chosen so that this mechanism is alpha LDP. This is the right probability to choose to ensure that. So we've taken the Sheffer test, we've simply passed the binary information through a randomized response, and then we come up with a corresponding private version of this test. Note at this point as well that this is the privacy mechanism, really. This is what's telling us how to generate the publishable data from the raw data, and this is very, very strongly tied to the specific problem that we're trying to solve. Here we're trying to test between P0 and P1, and we're looking at the set A that maximally discriminates these two distributions. This is crucial in this mechanism, and if we wanted to do something else with the data, if we wanted to estimate its mean, for example, this wouldn't be much use to us. This is only really useful for this specific task. Okay, so we've got the test. It's very simple to analyze this test. We can use Hoeffding's inequality here because all the random variables are bounded. It's very simple, and we can bound the minimax risk above like this. So if the total variation distance between P0 and P1 is above 2 epsilon and our sample size is large, then we have risk tending to 0. This is not quite the optimal threshold, 2 epsilon. You can see actually if you replace this critical value by this critical value here, then you can get down to epsilon divided by 1 minus epsilon, and this is optimal. The reason I don't want to do that is because this depends on knowing the contamination level. So if you just sacrifice a bit in the constants, then you don't need to know the contamination level. Okay, so this is an upper bound that's not difficult to prove. And of course, we want to know that this is optimal, and in fact it is up to constants. And I'll go through the proof here. It's short, but it has some very nice ideas. So I'll just say what kind of ideas we're using for these arguments. So I say there are 4 key steps, and I'll just talk about each one of them. So this first step is a standard minimax statistics step. This is a reduction, a kind of 2-point reduction. So we say that the testing error, I should say we're starting by choosing 2 distributions in our null and alternative hypotheses. So this means that we're choosing how to contaminate our P0 and P1. So we're making a choice here. This is a 2-point kind of argument. And then we say that the difficulty of testing between these 2 distributions is bounded below by 1 minus the total variation distance between these distributions. Now, it's slightly more complicated than in the standard theory because we have to pass these distributions through a privacy mechanism. So what this notation means is that we have n observations from M0, and then those observations are then privatized using an arbitrary mechanism Q, and similarly for M1. And then fixing the privacy mechanism Q, this is exactly the difficulty of distinguishing these 2 hypotheses. So this is standard, this first step. It's just that we have a privacy mechanism there as well. The next step is to use the Bretagnol-Huber inequality. So often we would just use Pinsker's inequality if we wanted to bound this kind of thing above, but it turns out that Bretagnol-Huber is much more convenient for this problem. We want things inside an exponent because, as we've seen, the error rates decay exponentially, so this turns out to be very convenient. The next step is perhaps the most interesting. This is due to John's work, John Ducci's work, and co-authors on general techniques for doing lower bounds for private estimation. So this is a very powerful result. What we're saying here is that the KL divergence between these privatized distributions can be bounded above by this quantity here. So there are a few things to say about this. One, the sample size n comes out the front, as we might hope for. So this reduces having to look at product distributions to having to look at individual distributions, which is great. The privacy parameter comes into it through this factor here, and we're mostly interested in small alpha, so this is approximately alpha squared. So this is kind of like a constant in our strong data processing inequality. We can think of these as kind of contraction inequalities. They say how the privacy mechanism makes distributions closer together, and the constant in that inequality is proportional to the privacy level squared. And also one very interesting thing, more from a technical point of view, is that we're able to bound a KL divergence by a squared TV distance. Now, if you were doing Pinsker's inequality or something like that, you would always be going the other way around. You would be bounding a squared TV distance by a KL divergence. And the fact that you can go back when you have privacy is the source of many very interesting phenomena in the theory of LDP. So we often see rates that are quite different for private problems compared to the corresponding classical problems. And I think this is one of the key reasons for that. You can go back from KL to the total variation distance and still get this factor of n out of the front here. So this is a very nice, more technical point. Okay, so now this holds uniformly in all privacy mechanisms that are alpha LDP. And so now we've removed this infimum, we've dealt with the privacy. And now it just remains to choose how to contaminate our initial distributions. I won't go through the details, but basically you choose contaminations to make these two things as close together as you can. And in fact, it's possible to choose contaminations such that the total variation distance behaves like this quantity here. So if P0 and P1 were close to begin with, it's possible to contaminate them to look the same. But if they weren't close enough, you can still contaminate them to make them look closer. And this is the kind of equality that we have there. This is kind of the best possible thing. So plugging this into here, we do indeed get the lower bound that we hoped for. So this matches what I was showing before, except we have this different factor here instead of a 2 epsilon, and the constant factors are different. But this essentially matches the upper bound that I gave before. So we have the optimal error rate, and let's just compare some different models where we might want to solve this problem. So classically, it's known that if you want to do point hypothesis testing, the Hellinger distance is the crucial quantity in the sample complexity. So, or if we want to think about things in terms of separation, we require separation between P0 and P1 in the Hellinger distance of at least this level in order to distinguish P0 and P1. The previous work, which in the pure contamination case was known previously, a lot of this was known previously, but if you just have contamination and if you have an infinite sample size, then you can distinguish these two things if and only if the TV distance is above this threshold. The reason I'm talking about infinite sample size here is it gets more complicated with finite sample sizes, and although Huber has found the optimal test for this problem, it's quite complicated to say exactly what its risk properties are. But when the sample is infinite, this is the exact condition to be able to distinguish these hypotheses. So again, Hellinger has changed the TV here. If you just have privacy, then this is the separation that you need to distinguish these two hypotheses. And if you have the combination of privacy and Huber contamination, then you simply just add these two thresholds together. So we have this very simple decoupling of these two aspects of the problem here. So in each case, so for each of these problems separately, you should compare a total variation distance to a threshold. And if you have both of them at the same time, you just add the thresholds together. So this is, it's a very simple decoupling. As another remark, yes, so as you can see from the test that I used, the privacy mechanism that we used was very natural, and it's a very natural way of privatizing an existing robust method. So given the methodology that was already out there in the robust statistics literature, it was very easy to come up with a private method. And I think that's a very nice thing about these areas. Often robust methods lead to private methods very easily. Okay, so that's about all I'll say about simple hypothesis testing. Now, the reason that we wanted to start with this problem, rather than maybe something more practical, is that there are these things in the robust statistic literature called tournament methods. So it's known that you can kind of come up with general theories for parameter estimation problems by considering hypothesis testing. So say that we've got a parameter space theta and we want to estimate a true parameter, then one method that we can use to estimate this parameter is to discretize the space into, say, theta1 up to theta m. And then for all pairs of parameters, we can compare them using a point hypothesis method. And then in those pairwise comparisons, we always have a winner. And then we just look at we choose the parameter that is beaten the least often. So you have a winner from these kind of tournament methods, and you choose that winner to be your estimator of the parameter. So this is a general approach to Huber contamination models that works without privacy. And so that's why we considered simple hypothesis testing first, because we wanted to do something like this. But in fact, it turns out that this will not work under privacy. And the reason is the following. So this is what's called a hypothesis selection problem, where we have a large number of hypotheses and we just want to choose one that fits our data the best. And it's known that without privacy, you can solve this if the sample size is at least comparable to this quantity here. So the sample complexity of this problem scales logarithmically in the number of hypotheses. This changes drastically, though, under privacy. So instead of having a logarithmic scale in M, a logarithmic scaling in M, we have a linear scaling in M. So this is really a huge difference between these two problems. Hypothesis selection is much harder under privacy constraints. And as a result, actually, the tournament method won't work. So this is just one example. So you can consider estimating the mean of normal data. Say it's just univariate. Then if the mean is in some bounded interval, the number of hypotheses we would have would be proportional to 1 over delta to get error delta. And the previous results show that choosing one of these hypotheses would require n alpha squared to be at least delta to minus 3. So this means that an estimator based on a tournament approach cannot do better than n alpha squared to the minus a third, whereas it's known, it's quite simple to show in this problem that you can estimate mu at the rate n alpha squared to the minus a half. So this is telling us that tournament methods don't work, and instead of using a tournament method, we have to come up with some problem-specific approaches. At least if there is a general approach, we didn't manage to find it, and we came up with some problem-specific approaches. Okay, so I don't think I'll have time for the third and fourth problems, but that's fine. I'll just talk a bit about mean estimation and finish there. Okay, so we're going to consider a kind of robust mean estimation problem. This is going to be univariate, so it's quite simple. We're going to consider, our model is going to be all distributions that have a mean mu that is in some interval from minus d to d. I'll talk more about this constraint later, but this turns out to be unavoidable. So we have a compact interval that our mean lies in, and we're assuming that our distributions have bounded kth central moments. So this is kind of a very heavy-tailed mean estimation problem. And we aim to estimate this mean under squared loss. So the result, the upper bound, is that we can construct an estimator that has this error guarantee provided this condition holds. And in fact, this is optimal. So we can see that this is optimal. So again, we have this decoupling between a private rate and a difficulty due to contamination. As in the other problems we consider, these things appear separately in the literature. So this is known to be the private rate for estimating a mean. This is known to be the difficulty due to contamination. What we did that was new here, though, is we really wanted to look at the dependence on D in these rates. So this is something that has been noted previously in the literature, that in private problems, you have real issues with large parameter spaces. It feels, it's kind of unsatisfactory. You'll feel like it shouldn't matter where your mean is, but it turns out that specifically in local privacy, the minimax risk would be infinity if you had an unbounded parameter space. If you didn't know anything about the location of your mean, you just wouldn't be able to estimate it. We need to know something about the location of the mean. So we assume that it's bounded between minus d and d. For a constant value of d, what you can do, and what John has considered in his work previously, is to use a simple Laplace mechanism. So say that our data is bounded between minus d and d. We can truncate it to some interval minus m to m, add the corresponding amount of Laplace noise so that this is private, And then it's not too difficult to see that if we choose M appropriately, the error of this estimator is going to behave like this. Now this is optimal for constant D, but this is very much suboptimal if D grows. What we do instead is we consider a two-step procedure. So with the first half of the data, we first get a very crude estimate of the location of this distribution. So we start by basically forming a noisy histogram. We form a private histogram of our data where the bin width is constant order. So we have these big bins that don't allow us to estimate the mean consistently, but they give us a rough idea of where this distribution is in space. So once we've kind of decided on a bin that looks likely for our distribution, we then apply the previous Laplace mechanism kind of restricted to that bin. So we're choosing a crude location first of constant order width, and then we're applying the existing procedure on that constant order interval. And it turns out that this is optimal. So as long as log d over n alpha squared is bounded above by a small constant, you can get a rate that's independent of d. Right, and yeah, this is optimal, as I said. So that gives us this condition here, and you can see that if this condition, well, we can prove that if this condition does not hold, then again the minimax risk is, the minimax risk will be infinity, or the minimax risk will be very large. Okay, so we consider this two-step procedure, and this gives us the optimal dependence on D and the rest of the parameters. I should say, just briefly, so this is an interactive procedure because the way that we privatized the second half of the data depended on the results from the first half of the data. So the first half of the data told us a rough location, and then we privatized based on that. It is possible to do the same thing with a non-interactive procedure, but it's much messier, so I chose not to present that here. Yeah, you can see the paper if you want to see how we do that. It's a similar idea, but there are technicalities that you've got to deal with. Okay, so I'll skip through the other two problems, but just to say we do have a kind of similar decoupling between rates, and I'll just go to a conclusion now. Okay, so we've considered a few problems, and in each of them we find procedures that are both privacy preserving and optimally robust in each of these problems. Often these estimators that we use either come from the robust statistics literature and then we've just adapted them to be private, or sometimes, as was the case for density estimation, we just took estimators that existed in the private literature and showed that they were also robust. So you didn't have to alter these estimators, they were automatically robust against contamination. So there are a lot of ideas between these two literatures that can be shared, and ideas that can help us to come up with good methodology. As I said, we wanted to come up with a kind of general theory that we thought we would be able to base something on hypothesis selection, but this turned out to be one difference between the non-private and private cases, that hypothesis selection is just much harder under privacy. And yeah, I've basically covered the last point already. So yeah, thank you very much for your attention. This is the main reference. Thanks.